Alright, so here in this particular first problem of this video, it says the work function of some metals are listed below. It says which of the following, which of the given metals will show photoelectric emission when illuminated by light of wavelength 240 nanometers. So here we have lithium, which requires at least 2.4 eV electron volts, copper 4.8, silver 4.3, potassium 2.3, and then magnesium, which is 3.7 electron volts. Okay, so in order to figure out which electrons or which material will give off electrons or emit electrons, you have to figure out how much energy is coming in. So in this particular problem, it states that the incident wavelength here is 240 nanometers. So knowing the wavelength, you can find how much energy that particular wavelength of photons carry. So I'm just going to go ahead and set up. So E, which is energy incoming, equals KE plus the work function here. I just use W for work function here. Now, in order to figure out which of these metals will emit photoelectrons, you have to figure out how much energy is coming in. So we're going to go ahead and assume that KE is 0. So therefore, we can find the energy coming in. If that energy exceeds the work function, then we're good to go. Okay. So here on the left side, I just expand E equal to HF, Planck's constant times the frequency of the light that's coming in. And then on the right side, we set K is equal to 0. So the only thing left is the work function. So here essentially we have the statement. It says the work function is the energy coming in, right? So once we find this energy coming in and we find what this W is, if this W exceeds what's given here in the chart, then these photoelectrons will emit. If not, then they're stuck, they're bounded to the metal surface. All right, so on the left side, Planck's constant times frequency. However, I don't know what the frequency is. The problem gives us the wavelength of the incident ray, which is 240 nanometers. But what we can do is that we can break up frequency into speed divided by lambda. So hopefully by now you're familiar with these functions. So frequency is simply the speed of light divided by the wavelength of the incident ray. Okay. All right. So here we have Planck's constant, speed of light divided by the wavelength, and we go and crack this out real quick. Well, Planck's constant, you can look it up, but if you hopefully know it, it's 6.63 times 10 to the negative 34 joules times seconds. The speed of light, again, is 3.0 times 10 to the 8th meters per second. So H and C are both constants. The wavelength, however, is given in nanometers. So this is 240 nanometers, which you need to convert to meters because here in the top unit, you have units of meters for the speed, and there's also meters hidden in the joules here. So it's an indicator that you need to convert 240 nanometers to meters, which I did down here. So hopefully you know how to convert nanometers to meters. So if you convert properly, 240 nanometers is equivalent to 2.4 times 10 to the negative 7 meters. Now that you have everything in the proper units will cancel out. So if we simplify this on our calculator, you'll get 8.29 times 10 to the negative 19 joules. However, I do want to point out that the work function given here in the chart is in units of electron volts. The unit that I just found, is in joules. Okay, so what I need to do is convert joules to EV so I can make this comparison. So therefore, I just made a note for you here. Make sure you convert units. Again, this is in joules. The unit given in the chart is EV. So I'm just going to go ahead and simply convert 8.29 times 10 to the negative 19 joules to EV, simply by saying that 1 electron volts is equivalent to 1.6 times 10 to the negative 19 joules. So if you set up this conversion factor properly, you start with joules. So joule needs to go on the bottom. Joules and joules will cancel out. Therefore, the only unit left over here is electron volts. So you notice here in this one, it's a little easy. You have 10 to the negative 19 on the top here. You also have 10 to the negative 19 on the bottom, so those will cancel out. So essentially, all you have to do is really take 8.29 and divide it by 1.6, which will yield 5.2 electron volts. So now what do we do with this information, right? This essentially tells us that the incident ray is carrying 5.2 electron volts. Now, if you look at this chart, the minimum work function to eject these photoelectrons is 2.4, 4.8, 4.3, 2.3, and 3.7, which are all less than what you have coming in. So therefore, the final statement is all of these metals will have electrons emitted because they require less than what you have coming in. Again, the 5.2 eV is what we just found. So a wavelength of 240 nanometers will generate 5.2 eV, which exceeds what you need. So therefore, all of these metals that are listed in the chart will emit photoelectrons. Okay, I hope that helps. Let's do the next one. In this particular second example problem, it says in an experiment on photoelectric effect, a graph between maximum kinetic energy and frequency of emitted photoelectron from metal surface is found to be a straight line as shown below. And it wants us to calculate A, B, and C. So let's go ahead and crack out A. So here's Ke versus frequency. So you notice here Ke is in electron volts, not joules. Frequency here is in units of hertz, which is times 10 to the 14th. So whatever these values are, you would just have to multiply that by 10 to the 14 exponent. Okay, so keep in mind of the detailed work here. All right, so to find threshold frequency, all you have to do is look at this graph. So essentially this graph says, look, Ke is in the vertical axis, frequency is in the horizontal axis. For example, if you put in 5 times 10 to the 14th, don't forget these values here, you have to multiply by 10 to the 14 hertz, okay? So if you put in 5 times 10 to the 14 hertz, the light that's coming in is not strong enough to cause any kinetic energy. So at 5, Ke is still 0. So the frequency here is not strong enough. Now let's say, for example, if you go to let's say 7.5 where my cursor is, well, still nothing happens because if you go across, Ke is still 0, which means no electrons has been emitted, right? When electrons are emitted, they carry a certain amount of Ke, but this graph tells you that you have to go all the way up to where frequency is at least 10 times 10 to the 14 hertz, then something will happen. Photoelectrons will start, ejecting, okay? So therefore, from this graph here, I can conclude that 10 times 10 to the 14th is the threshold frequency. This is how much I at least need to put in. So the frequency of the incoming light must be at least 10 times 10 to the 14th. So any value bigger than 10 times 10 to the 14th will work. For example, like 15 times 10 to the 14 hertz will work because the frequency is now higher. Higher frequency suggests higher energy, and higher incoming energy will most likely emit photoelectrons. Okay. All right, so that's the answer for A. So just by this graph, the threshold frequency is where the slope essentially starts. All right, that's it. So here's a visual to help you understand this concept in case you're not keeping up. Just because you shine light doesn't mean photoelectrons are ejected. So as you can see here, this particular first diagram on the left, there is light coming in, but the light coming in has a low frequency than the required energy that's needed to cause these electrons to be emitted. Okay. On the right diagram, this is where quote unquote the threshold would be. So let's say example for the first one would be like the 5 times 10 to the 14 hertz. While you shine light, it's not strong enough. If you keep increasing the frequency, let's say to 10 times 10 to the 14 hertz for this particular element, then the incoming light has a higher frequency. Now once that frequency meets the threshold frequency, then electrons will start moving. Okay, so I drew here the velocity arrow really small. This would indicate that this metal surface here has had enough energy to cause the electrons to move. Okay, all right, let's go ahead and do part B. Part B wants us to find the work function in electron volts of the metal. So to find the work function, all I have to do is set up E equals K plus W. However, in order to find the work function, I can cross Ke out. Essentially, anytime I ask you to find the work function here, you can assume that is the minimum required in order to get these photoelectrons to move, because it is the minimum required. The electrons quote unquote hasn't moved yet, so therefore, because it hasn't moved yet, there's no Ke, so the Ke term disappears. All right. So on the left side, I broke up E into HF again. On the right side, I just left W as W because it's looking for the work function of this metal. Now that we know frequency of the incoming light, well, how do we know that? Because the graph tells us that the threshold frequency here is at least 10 times 10 to the 14th. So I can just simply say, well, I know Planck's constant, which is 6.63 times 10 to the negative 34 joules per second. Well, what frequency do I plug in? Well, I would just plug in the threshold frequency because it is the minimum that you need. Again, any frequency that exceeds 10 times 10 to the 14th to the right of this green dot will work. So therefore, what is the minimum work function? You just use the minimum frequency needed, which is 10 times 10 to the 10 times 10 to the 14 hertz. Okay. Once you simplify that on your calculator, you'll get a value of 6.63 times 10 to the negative 19 joules. But notice that in question B, or in part B here, it wants the work function in units of electron volts. So we just have to convert, once again, joules to electron volt. So Start with the joules values that you just calculated for the work function, which is 6.63 times 10 to the negative 19 joules. And then for every 1 electron volts, it is equal to 1.6 times 10 to the negative 19 joules. So make sure you put these values in the proper place in your conversion factor. Joules on the top, joules on the bottom cancels out. Once again, in this one, I'm looking at it, the exponent is 10 to the negative 19 on the top. You also have a 10 to the negative 19 on the bottom. So both of those will cancel out. So really, all you have to do is do 6.63 times 1, which is simply 6.63, and then divide that by 1.6 on your calculator, and you should get a value of about 4.14 electron volts. So again, the hard part's been done. This is just simply conversion. All right, so the work function for this particular metal is about 4.14 electron volts. That's how much you need at least. So let's say if you put in 4.15 electron volts, then electrons will move. If you put in 5 electron volts, then electrons will eject faster. Okay. Let's do part C. Part C asks us to find the kinetic energy if the frequency is 12 times 10 to the 14 hertz. So the minimum was 10. Now it wants us to find, well, how much Ke, or how fast would these electrons move out, right? Once we know the minimum, we know that any value be on 10 times 10 to the 14 hertz will work. So in this case, it gives us 12 times 10 to the 14th. So we know there's a little excess energy here. All right, so to find Ke, I'm just going to go ahead and algebraically manipulate the function to get Ke by itself. So there's a plus work function on the right side, so I'm just going to move to the left side, which makes it negative. So here to find Ke, we would simply take E minus W. Well, E is once again HF. The work function we already found, which is 4.14 eV from part B. Well, I know Planck's constant, which is 6.63 times 10 to the negative 14 joules times seconds. I know the frequency in part C. Part C tells us that the incident light carries a frequency of 12 times 10 to the 14 hertz. So that's the new frequency I'm going to plug in. I want to subtract that from the work function in EV that we found previously. But if you do your work correctly, these two first terms, HF will yield 7.956 times 10 to the negative 19 joules minus 4.14 eV. Now I highlighted joules and eV here because, again, you need to be super careful with your units. Here in the first statement you have joules, in the second statement you have eV. You cannot subtract these two values because they are not in the same unit. So it's important for you to write your units out as you practice these types of problems. Otherwise, you are going to subtract and get a whack-ass answer, okay? So here you would have to convert the 7.956 times 10 to the negative 19 joules into electron volts. If you've been keeping up with this video, I will leave that for you to do. So if you convert it carefully and correctly, you should get about 4.97 eV. The 4.14 eV stays the same. So really now we have both units in electron volts, so you can just take the difference. And the difference here between 4.97 and 4.14 eV would simply be 0.83 eV, and that is your answer for part C. So the kinetic energy would be 0.83 eV, and if a question asks you to find speed and stuff like that, you would just simply convert this to joules and then carry on with Ke is equal to 1/2 mv squared. Okay, I hope that helps. Stay nerdy, don't be whack.